Good afternoon, everyone. Welcome to our Lancaster Environment Centre first online seminar programme. For those joining us live, there are some important guidelines on the screen for allowing the seminar to run smoothly. Most importantly, keep your microphones and cameras off and post questions for our speaker using the chat function. That will enable our speaker to manage the question and answer session after the presentation. Also, very importantly, this session is being recorded and then we will be able to share it on our YouTube channel after the event. So for those joining us through YouTube, you are also very welcome. It's very nice to have you with us today. Now, to introduce our first ever seminar in our first ever online seminar series, I have the great pleasure of welcoming Professor Richard Betts MBE. It's a very appropriate seminar for today, the 50th International Earth Day, on the subject of climate change. What are we trying to avoid and what is inevitable? Our speaker, Richard, is Chair in Climate Impacts at the University of Exeter and Head of Climate Impact in the Met Office Hadley Centre. He was appointed MBE in the Queen's Birthday Honours List for June 2019 for his services to understanding climate change. His work has included cutting-edge research on climate change and advising governments as a lead author for the Intergovernmental Panel on Climate Change, the IPCC. He's very involved in public engagement with science, such as appearances on the BBC and ITV, sharing lots through social media, and also at Glastonbury Festival, which is how I've had the pleasure of working with Richard. In 2019, he joined us on our Sex, Bugs and Rock and Roll stall, where we were sharing climate change research and forest research with the festival goers through the medium of great activities and fun games. And one thing I learned through that experience is Richard is great to work with because he has never-ending energy. He'd be with us sharing the science, dash off to watch a band, come back, tell us all about the band, and then straight back into the science again. It was a really great experience working with you, Richard. So I'm really pleased to be able to invite you to give our inaugural seminar in this series. Thank you very much.
This is to explain how we project future climate change, the kind of future changes and impacts that we see under scenarios of ongoing emissions of greenhouse gases, the kind of things we're trying to avoid by reducing these emissions, but also the kind of things which are already locked into the system, even if we do manage to reduce emissions to the level of ambition suggested by the international agreements like the Paris Agreement and so on. So just as a brief introduction, of course, we are warming the planet, we are warming the climate. We're sure about this. There is vast amounts of data coming in from all around the world, regularly and routinely brought in for monitoring weather and helping with weather forecasts, but also monitoring the climate. So data from weather stations, satellites, buoys on the ocean, aircraft, ships, radio sondes, so weather balloons, all sorts. And that is collated into data sets which allow us to estimate the change in the global average surface temperature of the Earth. In the top right, this shows the Met Office version of that data set, but there's several other versions as well which give the same conclusion, which is that year by year we see temperatures getting a little bit warmer and colder than the global average, but overall in the long term, especially in the last 50 years, we've seen a long-term warming trend. And that's very clear, and that's seen not only in the land surface but also in the atmosphere as well. And we're seeing other signs of a warming world as well, such as melting of snow around the world, melting of the Arctic ice is covering less of the ocean, generally speaking, these days than it used to. Melting of glaciers, shifts in various species ranges and their phenology, the timing of their natural events, all consistent with a warming world. So we're certain the world's getting warmer. And this is caused by, at the moment, it's caused by increases in greenhouse gas concentrations, including carbon dioxide, due to people putting these into the atmosphere from burning fossil fuels and from deforestation and other things which release other gases such as methane and so on. The climate just changed naturally itself over centuries and millennia and millions of years, of course, but at the moment the cause of the rapid warming we're seeing at the moment is the additional input of greenhouse gases by human activities. And what will that mean for the future? That's the main job of the Met Office Hadley Centre and many other researchers as well, is to explain the past causes I've just done, but also look at future changes. And we do this using computer models, the same computer models which are used for the weather forecast, essentially. So these are mathematical equations turned into computer code, Fortran code in our case. There's about 2 million lines of Fortran, consists of the Met Office model used for weather forecasting and climate change. So it represents the flow of the atmosphere, the change in the water cycle, so changes from water vapor to liquid water in the atmosphere and rainfall, evaporation, so on. The global carbon cycle, changes in clouds, changes in the Earth's energy balance, including the greenhouse effect, as I just described, the effect of increased greenhouse gases. All these things are represented mathematically and then in the computer code. And as I say, this is essentially the same computer model used successfully every day for weather forecasting, but run for 100 years or more. Of course, we can't make weather forecasts for individual days more than a few days ahead, so we're not trying to predict individual weather events decades ahead, but what we can look at is long-term trends and the statistics of whether extremes are increasing or decreasing and that kind of thing. And to do that, we can drive these models with scenarios of future changes in the concentrations of CO2 and other greenhouse gases. So this figure shows the 4 standard scenarios used in the previous IPCC report, which was published a few years ago. So it's scenarios of concentrations, and the term is RCP, representative concentration pathways. So representative is important. These are not sort of predictions of future changes. These are kind of what-if scenarios to cover a range of possibilities, which have been worked out to be broadly consistent with different socioeconomic futures, but with lots of uncertainty in terms of the feedbacks in the carbon cycle from translating from the emissions into the concentrations. But these cover a wide range of possibilities, and they give you something to look at with the computer models to study a range of possible futures. But it is important to look at to compare these with what we think may happen with current and future emissions. And estimates have been made from organisations such as the International Energy Agency with scenarios of what current international policies, so different countries in the world have said about their energy policies, what they've actually enacted, the current policies, and their stated policies, what they say they're going to do. And these can be translated into scenarios of emissions, which can then be extrapolated into the future with various assumptions and turned into assumptions of concentrations in the atmosphere, which I've put on here in this sort of the wider plume there, which you can see is not at the highest scenario used by the climate community. That's important to recognise. The red line, the RCP 8.5, is not representative of what we expect from current policies. The current policies is more towards the second highest scenario, roughly speaking, but again, there's a large error bar in that. But so that gives you some context of the kind of things we can look at for different scenarios. And as I say, there's feedbacks in the system which introduce some uncertainty in this. And we can use those as input to the climate models, as I say, to then look at trajectories of future global mean temperature, as is shown here, and then the details of those around the world, as I'll show in some coming slides. So you can see that if we want to limit global warming to well below 2 degrees Celsius, as in the Paris Agreement, or even pursue efforts to limit warming to 1.5 degrees Celsius, which is the most ambitious part of that agreement, then we need to be following this scenario, which leads to the RCP 2.6 concentration pathways the dark blue line. And each of these wiggly blue lines there is a different climate model simulation from a different model. There's many different models in different centres around the world, which are looking at the impacts of that RCP 2.6 concentration. The number 2.6 is the change in the radiative forcing, the energy balance, change in the energy balance of the Earth at the end of the 21st century. So that's the kind of low emissions scenario, or one of the low emissions scenario to keep us below 2 degrees. There is a more ambitious one which is being looked at now, but I'm not showing that here. You can see though, if the ongoing emissions scenarios give a faster rate of rise, the highest one, this RCP 8.5 scenario, as I say, is above what we expect from current emissions, would give warming of anywhere between about sort of 3 and 6 degrees Celsius by the end of the century. But if we look at what would be expected from current policies, that's more between about sort of 2 and 4 or so degrees Celsius roughly. Again, with probably large uncertainty around that. But you can see that with current policies, we can expect to see global warming exceeding the Paris Agreement target of 2 degrees Celsius, most likely, and possibly up to 4 degrees warming relative to pre-industrial, or possibly a bit more. So it's worth looking at what those levels of global warming would mean in terms of impacts for people. There's a 4 degree threshold there, just to clarify that. So one of the obvious questions is, could it get too hot for humans? It kind of stands to reason that if the world gets hotter and hotter and hotter, sooner or later we will start to reach the physiological limits that we have as mammals. We've evolved under certain ranges of climates. We can live in a whole range of climates around the world, but could it get too hot in some places? An important point is it's not just about temperature, it's also about humidity. As you're probably aware, that a wet heat is more uncomfortable and more dangerous, more conducive to heat stress than a dry heat. When it's very humid, you can't sweat and cool down your body so much, and therefore you're more likely to be stressed from heat stress under wet heat, high humidity. And that can be quantified in terms of various industry standard metrics. A very commonly used one in various industries uses a metric called wet bulb globe temperature, which combines the actual temperature and humidity and solar radiation to give a measure indicating the risk of heat stress. And this particular table here is used by the US military to show when outdoor training needs to be limited or prohibited. And some important numbers to remember here are that 28 Celsius wet bulb globe temperature is regarded as high heat stress when you need to reduce outdoor exercise, and 32 Celsius wet bulb globe temperature is extreme heat stress when physical exercise training is banned, basically, because it's just too dangerous. So we can look at the occurrence of those kind of high temperature and humidity situations under the current climate, and this shows, based on observed data, that we do get sometimes, occasionally, these a few days per year in some parts of the tropics and subtropics where the wet bulb globe temperature, the maximum wet bulb globe temperature, exceeds 32, this extreme heat stress metric. So those blue squares in parts of Africa and the Indian subcontinent are showing where there's a few days per year exceeding that. If we look at our computer model projections, future climate, and go out to 2 degrees global warming, and this is looking at the average of several models, you can see that across quite a lot of North Africa in the Sahel region, and quite a lot of most of the Indian subcontinent, parts of Southeast Asia, parts of North and Australia, and some parts of South America and Central America are seeing areas where there's perhaps about 5 to 10 or 20% of summer days exceeding this extreme heat stress in the wet bulb globe temperature max. So you'd consider that to be extreme risk for several days per year. And if we go on to a 4 degree global warming world, then that situation extends across basically the whole of the tropics pretty much, and large parts of the subtropics as well. And you can see that some areas actually for 80% of the summer or more, like in Northern Africa and the Indian subcontinent, Northern Australia, Papua New Guinea, Indonesia, you can see this 80% of the time is seen as extreme heat stress risks, and around 20, 30, 40% of the time across much of the tropical land. So these countries would be finding it difficult for people to be outdoors and certainly work outdoors for quite a lot of the year. So that's a sort of severe risk at that level of warming. So that suggests that yes, it is possible for global warming to reach levels where it is, becomes impractical really to function outside of an air-conditioned indoor environment, and with consequent implications for could we even the issue of sort of human mortality is more complicated. You wouldn't sort of necessarily die immediately under these high temperature and high heat stress things, but it makes it the increased risk from heat waves would be more severe under these conditions. So the other question is what's going to happen with the water. Will it be wetter or drier? And that gets more complicated than just looking at temperatures. We want to know will we see increased drought, will we see increased flooding? But that's much harder to predict with the computer models for certain. We know that changes in temperature will change rainfall patterns. A warmer world on the whole holds more water in the atmosphere. You also get more evaporation. So overall, we expect more rainfall on the global average, but some areas will see less rainfall and less snowfall because of changes in the atmospheric circulation, bringing less rainfall. But different models give different answers as to what they predict will happen and future warming. So these two figures here show two particular outputs of two models. You can see that there is some agreement in some places. So the far north, for example, is predicted in all models to have an increase in precipitation. The Mediterranean region is always predicted to have a decrease in precipitation, but other regions, such as South America, for example, it could go either way. In eastern Brazil, for example, you can see there's an increase in rainfall in the lower model, but a decrease in rainfall in the upper model. So we have to look at a range of possible outcomes for changes in rainfall when considering impacts on flooding and drought and so on. Generally speaking, when droughts occur, we expect them to be more severe. So even though on the global average we'd expect more rainfall, where it is drier, we'd expect the droughts to be more severe when they occur. And when it's raining, we expect rainfall to occur more heavily as well, because a warmer climate drives more intense thunderstorms, for example, more intense convection. So when rain comes, it'll fall more intensely. So we can use the output of climate models to drive other models which can do things like looking at impacts on river flooding. And this shows the output of one study which used a set of climate models to look at the number of people affected by river flooding, which currently is around 54 million people per year. If we look at 1.5 degrees global warming and put the change in rainfall through this river flooding model, that 54 million increases by 24 million to about 78 million people per year affected by river flooding. But the error bars are fairly large. It's between 39 and 122 million people per year. And on the map, the colours are showing the percentage increase compared to the present day of the number of people affected by flooding at the level of individual countries. And where it's hatched in grey, that's showing there's not really a consensus on the change, enough to show on the map there. If we look at 2 degrees global warming world, then the numbers increase further. There's an extra 43 million people affected by river flooding compared to the present day. So the number in total is up to around 97 million. So that's about an 80% increase compared to the present day. And if we go up to a 4-degree world, you can see many countries in the world have seen more than 100% increase in the number of people affected, perhaps even up to 400% increase, leading to, in the global average, an extra 157 million people affected by river flooding, so over 200 million in total, anywhere between about 111 and 35 million. So overall, most countries would expect to see increases in people affected by river flooding. This is all in the absence of any adaptation, incidentally. This is all under, with current levels of flood defences. If there was investment in improved flood defences or flood management, that would reduce the actual impact of this. But this is showing the changes in the climate hazard, as it were. And then the other cause of flooding which we can consider would be due to sea level rise, which is a no-brainer in terms of a warming world. We're already seeing sea levels rising. This happens for two reasons. One is the melting of ice, and also it's the fact that water expands as it warms as well. So both these things would be expected to cause an ongoing sea level rise. And this figure here shows again computer model projections of sea level rise under this is the second highest emissions scenario and concentration scenario, greenhouse gas concentration scenario that I showed earlier on. So the one which is closest to the current emissions scenario. And you can see it's broken down into the different components of sea level rise, the different areas of ice melt, glaciers, Greenland, Antarctica, which has a small effect at the moment, and thermal expansion, so the expansion of the ocean waters as they warm, which is the largest component actually in this century. And the grey plume and the black line in the middle is the projection of the total sea level rise. So anywhere between about nearly 40 centimetres and say 70 or so centimetres sea level rise by the end of the century, and I'll explain what that might mean in a later slide. So that's for the ongoing emissions scenario, but it's important to note that this would happen even in the scenario of reduced emissions. I talked about the RCP 2.6 scenario earlier. This is the one which is keeping warming below 2 degrees under the Paris Agreement. And even with that scenario, so even with rapid reductions in emissions, we would still be committed to ongoing sea level rise, because it takes a long time for the system to fully respond to the changes. It takes a long time for glaciers to melt to a new equilibrium. It takes a long time for the heat to penetrate into the deep ocean. So even with rapid climate action, we'd expect to see ongoing sea level rise to some extent, between about 30 and 60 centimetres by the end of the century. This could be lower if there was even more drastic emissions cuts to try and limit warming to, say, 1.5 degrees Celsius, the more ambitious target, but even then there would still be ongoing sea level rise. So that shows that some sea level rise is already locked in, and therefore it's important to be being prepared to adapt to that. It's also important to look beyond just this century, because sea level will continue to rise, and if we follow the medium high emissions scenario, which I showed earlier, so this is the one which sort of not the very highest, but the second highest. If CO2 concentrations stayed at about that level reached by the end of the century for the next 500 years, the sea level would rise globally anywhere between about 1.5 and 7 metres globally. So we could be committing future generations to very large increases in sea level. And just as an illustration of what that might mean, I mean, this has been studied for many places around the world, but one place which is well known to be particularly vulnerable is Bangladesh. And the work I'm going to show now is done by a team at Bangladesh University of Engineering and Technology, who I worked with in recent years. And they looked at a scenario of if a previous storm which hit Bangladesh in 2007, cyclone Sidr, if the same storm was to hit again, what would the impact be under higher sea levels in the future? And this table shows the impact of the actual storm in 2007. It inundated an area of 1,484 kilometres squared, which was 1.2% of the country, and it affected 1.9 million people. It didn't kill that many people. Luckily, they have good adaptation in place now. They have storm shelters, so with enough warning, people can retreat to storm shelters, which are basically concrete buildings on stilts. So as the floodwaters come in, people can retreat to these, stay out of harm's way mostly, and then when the waters have receded, they can go back. But then obviously their houses have been destroyed and so on, so it impacts them, but this is not people killed. The point of this study is to look at where more storm shelters need to be put in place as an adaptation measure. So if the same cyclone was hit again, but if sea levels had risen by 0.5 metre, which, as I say, may be already committed even under low emission scenarios with emissions cuts, and probably is the minimum we could expect under a higher emission scenario, the area flooded would be more than doubled and affecting more than 4 million people instead of 1.9 million people. If the sea level had risen by 1 metre and that storm happened again, which could just about happen this century under if there were stronger feedbacks or higher emissions, or if the sea level responds more rapidly than we expect due to loss of ice and so on. But 1 metre could happen well within the early part of next century. That would inundate nearly 6,000 kilometres squared and affect 7 million people, so much wider area, 4% of the country. A 1.5 metre background sea level rise, maybe by the end of the next century, would affect 9.1 million people. So you can see the number of people affected and the area affected would be magnified a lot by the same storm coming in if sea level has already increased as it's projected to do so. So that was just some examples I wanted to show. This is obviously a quite fairly short seminar for covering all of climate change, so I won't attempt to cover any more than that. I'm happy to take questions on other impacts if you're interested. But to summarise, if we continue with current emissions from energy production, transport and so on, we'd expect to reach global warming of between about 2 and 4 degrees Celsius by the end of the 21st century, or it may be higher than that. A 4-degree global warming world would lead to high risk of heat stress across much of the tropics and increase both drought and flooding risk. The numbers are hard to pin down on that, particularly in individual places because of large uncertainty in rainfall patterns, but we'd expect approximately an extra 150 million more people to be affected by river flooding per year in a 4-degree world. Sea level rise will continue even if we have rapid and deep emissions cuts, and will continue more if we don't. So this will magnify coastal flooding that already occurs due to storm surges from cyclones and so on, and could eventually lead to gradual inundation as well. So we do need to be adapting to some level of unavoidable change, although we can avoid the worst changes by reducing emissions. And that was all I wanted to present, so I'm happy to take any questions. And I will look at the chat for this. Okay, thanks. I can see the questions coming in. Thank you. So someone's asked for more details about the models. I'm not sure exactly what details. There's a lot I could say. Perhaps if you put a more specific question in about what details you're interested in, I can address that. Another question would be, would future temperatures predict changes in population distribution? Probably yes. That's very hard to make quantitative predictions, although a group I've worked with at the University of Liège in Belgium do look at environmental migration, and they actually work with local communities in many places around the world where people are already moving and migrating because of how they're seeing climate change. Often it's down to what their perception rather than actual measurements, which is, as you'd expect, because people just react to what they can see. So it is expected that changes in climate would lead to changes in migration. I guess the most obvious one would be coastal flooding and repeated inundation and so on. There's highly populated areas, particularly around the coast of Asia, which would, which as I've shown, would be flooding more. Some communities are resilient to some level of flooding, but sooner or later it would be a lost cause. So it's hard to say how many people, but I think it's inevitable that sooner or later people will be moving in large numbers because of climate change. Right, a lot of questions. Thank you. This is great. I'll just sort of pick a few which happen to catch my eye. So someone asked about if we stopped all emissions right now, would there be a carrying of changes put in motion? Yes, there would. There would still be a bit of warming. And actually, if you did actually completely stop emissions immediately, there would actually be a warming suddenly, because the fossil fuel emissions not only increase greenhouse gas concentration, they also put aerosol pollution, so sulfur dioxide, into the atmosphere, which has a cooling effect which slightly offsets the warming of CO2. So there'd be a warming shock if you literally stopped emissions right now. That's unlikely. It's more likely to be scaled down. But there would still be some warming locked into the system, even with very rapid emissions cuts. Someone said, what extent are clouds incorporated in the models? They are included. They're one of the most challenging parts of the models to get right. So clouds have both a warming and a cooling effect, depending on how high they are in the atmosphere. Higher clouds have a warming effect, lower clouds have a cooling effect. And cloud in the night has a warming effect because it's not reflecting any sunlight away. There's a lot of work being done to understand and predict these, often through aircraft-based studies and so on, to understand the cloud microphysics, and also increasing the resolution of the models so that you actually resolve clouds at the scales that they are, a few hundred meters or a kilometre or so, rather than having to approximate them in grid squares of several kilometres or several tens of kilometres, which is often done. There's a question about the isostatic adjustment in sea level rise prediction. Yes, that is taken into account. So that's the change in the land in response to the coming out of the last ice age, for example, and the loss of the weight of the ice. So land changes, they are taken into account in sea level rise predictions. What have we got? But I won't be able to answer all of them, I'm afraid, because there's quite a lot, but thank you. There's a question here about what does the COVID-19 pandemic taught about how governments decide to respond to risk. That's a really interesting one. I've been thinking a lot about that. The pandemic and climate change, the response relies both on modelling to predict the future and observations to show what's happening. And in both cases, by the time you've got enough observations to see what is really happening, it's too late to take action to head it off completely. The the models that were used to predict the pandemic did show increased numbers of people affected by it. I think most countries, if they'd responded immediately, could have reduced the impact. And it's the same. And if they hadn't, if they didn't respond as much, then they're seeing larger impacts. So relying on that is an important part of it. But of course, you're making decisions in the face of uncertainty because models are never perfect. I've talked about uncertainty in these models here, and the same is true in epidemiological models as well. So it's a challenge of making decisions in the face of uncertainty, and people often don't really act or take it seriously until they see the thing happening in front of their eyes. And I think the same is probably true of climate change. We've been predicting, climate scientists have been predicting for decades that warming will happen. Predictions released in the early 70s were fairly accurate about the level of warming that's actually happened. There was a Met Office paper which predicted 0.6 of a degree Celsius warming by the year 2000. The actual warming was about 0.5. So good predictions were made, but we're still impacting the climate, and now we're seeing the effects happening that were predicted. So I think there are lessons to be learned about how to make use of scientific models and observations and making decisions in the face of deep uncertainties. There's a question about loss of biodiversity. That could play a role in the carbon cycle. I very briefly mentioned carbon cycle feedbacks earlier in the talk about the challenge of translating emissions into concentrations in the atmosphere, because the buildup of CO2 in the atmosphere is affected not only by what we emit, but also how much is absorbed by land ecosystems and by the oceans. And there's natural exchanges in both directions between the land and atmosphere and ocean and atmosphere. But these changes are affected by climate, and that can cause a feedback on the system. And the land feedback probably would be affected by biodiversity to some extent. I'm not sure if that has ever specifically been quantified as to what the carbon cycle feedbacks would be from a given loss of biodiversity, but I think changing the makeup of an ecosystem would have some kind of a feedback. And somebody has asked about climate skeptics. I'm just trying to come back to that. And naysayers. Do I encounter such people? Yes, all the time. And I do think it's important to address genuine questions about the science. Sometimes people will come quite rightly asking, is your model really robust? Have you quantified the uncertainties correctly? Are you confident in the data? And that's all fine. And it's important to not ignore those kind of challenges. But you also do get questions and challenges coming in, not exactly challenges. You just get the same things being said over and over again, which have been addressed many times, which I'm less enthusiastic about dealing with, as most people would say, would agree with. And this can be from people from all walks of life. So the question here is about politicians, but also members of the public and people from industry and so on. I have been involved in correcting incorrect statements which have been made by politicians and others in the media when they said something inaccurate that hasn't been challenged. Then that's sort of gone through to complaints against the broadcaster and so on. And actually that can happen in either direction. It's sometimes people campaigning for climate action will also say inaccurate things, which reduces the credibility of their cause. So they have to be careful as well. So scientists can play a role in making sure that people on both sides of the debate are sticking to accuracy, and obviously people have different opinions about what to do with it, but it's important that science is always accurately represented in the media and in politics. What are the So we asked about the flooding slide and the UK. So the river flooding is a particular issue in the UK already. One of my roles is leading the science assessment for the next UK National Climate Change Risk Assessment, and flooding features in that quite a lot. One of the purposes of this climate change risk assessment is to inform adaptation, so that we can prioritise investment in adapting to the unavoidable impacts of climate change. And both river flooding and coastal flooding are an area where that it is been shown up in previous assessments and is already the national adaptation plan, but that clearly needs to be an ongoing issue and further examination, especially as we improve the models and we find that intense rainfall may be more likely than we thought previously as well. That's one of the important new results coming out of the latest models. I think I'm coming close to the end of the 45 minutes, so I'll just look if there's any other questions I've missed. Somebody asked about the challenges of combining models together, which is a really good question. So I guess there's two ways you could look at that, actually. I don't know whether you mean looking at several different models which are doing the same thing and trying to look at the range of outcomes, or whether you mean looking at different models of the system, so the atmosphere and the biosphere and the ocean. But I can say something about both of those. So yes, on the first one, because we can't perfectly model and perfectly predict the climate system, we do use a range of different models from different centres, and there's different ways of combining the results. One is what you might call model democracy, where you assume that each one has an equal chance of being correct, and then use that to give you a spread of possible outcomes. But of course, not all models are equal. Some will be better than others, and there's a lot more work done these days on trying to constrain the models and focusing on the ones which are more accurate in terms of their simulation of the present day and recent changes. But that's not always as easy as it might sound, because the changes we're predicting in the future are outside of what we've seen in the past, so you can't always constrain them as much as you would like. And then the other challenge is linking together different models of the system. So there's atmosphere model, ocean models, biosphere models, and so on. And often studies will use like a one-way chain going from the atmosphere model to the flooding model, which I showed. Often studies of biodiversity and ecosystems will do the same thing. So have the climate change impacting the biosphere, but in reality, in the real world, the biosphere feeds back on the climate, so you want to include all those as well. So trying to get these to be consistent is quite a challenge. But the difficulty there is often because the climate models, again, aren't perfect in the present day. You often apply an adjustment when you link it to the offline impact model, so that your simulation of the present day is real, and that makes things inconsistent. You kind of break the conservation of the water cycle, for example, so that's not ideal either. So there's a lot of challenges there as well. So it's gone 1:45. So Ali, is it now time that we finish?
I think that's you've done very well with answering an awful lot of questions there, Richard. Okay. So thank you very much indeed. Okay. So all that remains for me to say is thank you very much to everyone that's joined us. I think we got there, the odd technical hitch along the way, but I think we got there overall. And thank you very much for taking the time out to present to us today, Richard. It's been really appreciated. I feel like I have to do a round of applause by myself, which is a little bit weird, but
thank you very much. yeah, I've enjoyed it. Thanks for all the questions. It's really interesting. Thank you. Thanks for having me.